You're muted. Your microphone is muted.
Can you hear me now?
Yes.
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 Awesome. So we are recording. Thank you for coming to my fun demonstration of temperature and density. And this is a lesson that I have taught to 6th graders. It's been a couple years, but I think students of any grade would find this an interesting way to explore the concept of heat rising. And as I'm proceeding, if you have any questions, please feel free to unmute and ask them verbally or put them in the chat. And here we go. So today we're learning about density. And if I were in the classroom, that would be nice because it wouldn't be backwards. And so let me see.
Don't worry.
Brenda-Jean, it's not backwards for us.
not
It's only backwards for you.
Oh, okay.
So, but I can't see it at all. It's maybe because it's
I can see it says density.
okay.
And it's not backwards?
No.
No,
Okay.
I can see it.
Awesome. I do have 2 cameras going, so fun with 2 cameras. So the thing about density is that it makes me think of a rock. If I throw a rock into a pond, it's going to sink. And the reason why is because the molecules in the rock are very close together, and that makes the rock heavy or dense compared to the water. And things that are heavy sink. Whereas if there was a foam toy, a noodle, for instance, it would float because the molecules in the foam are spaced further apart, and that means they are less dense. Does anybody know a word for less dense? It would be the opposite of density, and it starts with a letter B. And you can say it verbally or you can put it in the chat. I see the word buoyant, which is an adjective, which is the opposite of dense. And so we can make that into a noun by calling it buoyancy. And hopefully I have spelled that correctly, even though I'm nervous. So today we're going to talk about how temperature affects density and buoyancy. And we're going to do it with a liquid, which is one of the 3 states of matter. Can somebody tell me what the other states of matter are besides liquid? Go ahead and put it in the chat. We have solids and liquids such as water, and we also have gases. And so today, the liquid that we're going to work with is water. And so very conveniently, I have some hot water, which has been heated up by a handy tea appliance. And I'll be right back. My cold water has been sitting in the refrigerator, getting very, very cold. And I even have some ice cubes to make it even colder. And I have created a little diagram for you to tell you about the molecules in the hot water. Heat is a form of energy. It's similar to another form of energy, which starts with the letter K. And does anybody remember the form of energy that is the energy of movement, which starts with the letter K? What kind of energy is the energy of movement? kinetic energy is a type of energy when things move. Well, today we're going to be talking about heat energy. So let me throw that up on the board. And heat energy is similar to kinetic energy in that it is molecules moving. When you have heat energy, a substance, a solid or a liquid or a gas, it makes the molecules in the subject in the object move around. So if you have water like this, all your molecules are running around and they're bumping into each other and they're pushing each other farther apart because they have a lot of energy in them. Whereas if you have cold water, the cold water has less heat energy. And since it has less heat energy, all those molecules are not moving around fast. In fact, they're just sitting there and shivering, and they'd like to be very close together because they have less heat energy. So things with less heat energy are more dense. So I'm going to put some hot water into this clear container here. And you can tell it's hot if you see the steam rising. And I can feel that it's hot with my hands because the plastic container doesn't insulate very well. And now I'm going to pour some cold water into this similar container. And the hot water and the cold water look exactly alike because they're both clear. So in order to distinguish between the hot water and the cold water, I'm going to put some food coloring. And I've chosen to go with red food coloring for the hot water because in my mind, I associate red with hot. And you see how that red food coloring is diffusing down through the water. And I'm going to put some blue food coloring in the cold water because I associate blue with being cold. And you can see how that blue is diffusing nicely down through the water. Now, what do you think would happen if I were to tip over the water excuse me, while I'm looking for a very important component of my experiment. Which is a playing card. So I'm going to put the playing card on the lid of the container of red water, and I'm going to flip it over. And put it on top of the blue. And what do you think will happen when I take the playing card away? If you have a theory or a hypothesis or a guess about what will happen, go ahead and put it in the chat. What do you think will happen when I take the playing card away? What happens when you mix red and blue? Okay. And if anybody wants to unmute and respond, let me know what you.
Purple.
Okay. So do you see purple, or do you still see red on the top and blue on the bottom? And if the red stayed on the top and the blue stayed on the bottom, why would that be? And how would that be related to these diagrams where I've shown that the hot water, the molecules are far apart, and with the cold water, the molecules are closer together? If anybody wants to unmute and respond verbally, you can.
So the blue water is more dense, so it's going to settle to the bottom.
Well, so Peter has said he has used our vocabulary word that we introduced today about density. He said the cold water is more dense, and it's going to settle to the bottom. Do you think that this diagram where the molecules are closer together, do you think that that might weigh more than the diagram where the molecules are farther apart?
No,
Okay.
it's the
So-
same volume. It's the same volume of water, pretty much. So it would weigh the same.
Well, I would like to suggest that that is what you would expect, because you see two bottles, which, as Jamie has pointed out, their volume is the same. The bottles are the same size. It is the same amount of water filling up each bottle. But I would like to suggest that if the molecules of the water are actually farther apart because they have a lot of heat energy, which makes them move around and push each other, and the molecules in this water are closer together, that this water actually weighs more. It is more dense. It sinks. And so does that description, which I've just said, does that match what you're seeing in the bottles of water, where the blue water has stayed on bottom and red water has stayed on top?
Could. What about an explanation that the red and the blue can't change because both bottles are full and there's no place for the water to change to go to?
Okay, well, in order for us to test that theory, that maybe the reason why the red has not gone down is because of water pressure, which is something that we haven't learned about yet. So can anybody think of a way that we could figure out whether Jamie's hypothesis is correct? If you have an answer to an idea, you could put it in the chat, or you could unmute and express
Just
it verbally.
reverse the bottles.
Yeah, I was
Okay.
thinking,
So it sounds
Right.
like,
put it down and see what
Flip
happens.
it, flip it over.
Carefully.
okay, I'm getting some suggestions to try the reverse. So here we go with our cold water. When I'm nervous, I lose things. Or forget to put the lid on things. So once again, I have a container, and all of these containers are the same size or the same volume. They contain the same amount of water. So the only difference between the water is its temperature. And if I don't put the food coloring in, we don't really have a way to gauge its temperature. So once again, I'm going to put the red food coloring in the hot water because I associate red with hot. And I'm going to put green food coloring in the cold water because I associate blue with cold.
If you were to weigh those two bottles, then separately, we could see how, even though they had the same volume, then one would weigh heavier than one would weigh more than the other.
I wonder if a regular scale like we use in the bathroom would indicate that difference, or if we'd have to have a very sensitive scale because molecules are so small that the weight would be hard to measure, but this demonstration is one way that we can figure out without a scale. Okay, so now I'm going to flip over the blue one and put it on top of the red one. And what do you see happening to the red and blue?
They're mixing.
Purple.
So, okay, now with this one, with the second experiment, which one did we put on top? The hot or the cold?
The cold.
Okay, and what color was the cold?
Blue.
It was blue. And where has the blue gone?
Down.
It's gone down and it has mixed with the red. Whereas with our other set of bottles, okay, there's going to be a mess in a minute. As you can see, it still has not gone down, although the temperatures are probably getting a little bit closer.
So if you were to leave that first one long enough, we'd expect the colors to mix.
Well, Jamie, what do you think would happen? What happens to hot things when you leave them out for a while?
Yeah, well, the hot thing would cool and the cool thing would warm and the temperatures would be not so different. So the densities would be not so different.
Mhm. So if we wanted to stay in this experiment for a while, we could check and see how long it would take for the temperatures to become similar and for the colors to mix. But for the purposes of our demonstration today, we are done. I'm going to pop into the chat in case anybody ever wanted to do this same demonstration. These are the components that I used for it. Now, the tea appliance is more convenient for my purposes here today. And if I was in the classroom, that would work better because I wouldn't have a stove to heat up the water. And ice cubes or refrigeration helps make cold water. And towels, definitely a good idea. Alrighty, guys. Does anyone have any questions about density and heat energy?
It's very clear.
Well, be sure to tune in next week when we talk about the effects of temperature on a gas.
We can't wait.